So I'll be talking about models of dialogue and conversation. This is something that I used to do a lot, but I haven't done a whole lot recently. So if there are other people in the class who want to pipe up about interesting things that you've heard recently, then I'd be happy to cover this or to discuss this as well. That being said, I have worked on dialogue before, so I do know a fair amount about it and feel I can cover it reasonably well. Okay, so for dialogue, dialogue is a conversation between multiple speakers, and there's various types of it. Then there's a question of who is talking. There's human-human dialogues, which we might want to process with computers to analyze them to figure out what's going on in them. There's also human-computer dialogue where you're speaking with an agent here. So there are dialogue analysis tasks in the first part, and also things like dialogue generation tasks in the second part. And also, you can break it down into why are they talking. So there's task-driven dialogue, which is where you are conversing to solve a particular task, and also chat, where you don't have any particular task, except maybe your task is to make sure that the person you're talking with doesn't get so bored that they don't want to talk with you anymore. So these are two very different things. In reality, probably when people want dialogue agents, they want a little bit of both. They want something that can help them out, but maybe also entertain them a little bit as well. And most of our agents that we have do that. So because models of chat are a little bit easier and the systems tend to be a little bit cleaner, I'm going to talk about them first. And within this, there's kind of two paradigms. There's generation-based models, where they basically take an input and generate an output. These are good if you want to be creative and come up with entirely new utterances, for example. There's also retrieval-based models, which take the input and find the most appropriate output. And these are good if you want to be safe, if you don't want to generate anything that is ungrammatical or maybe generate anything that's inappropriate for the situation or something like this. Which one you choose depends on how ambitious you are. Perhaps the generation-based models basically are assuming that the model will be able to generate something new that actually makes sense. The retrieval-based models kind of lie on the assumption that nobody says anything new and interesting, so you can just have a conversation by repeating things that other people said. That's probably true to some extent, if you're talking about like what machines can actually generate, but who knows? So I'll first start talking about generation-based models. And generation-based models actually started out maybe around 2011. And the way people created them was training machine translation systems to perform translation from utterance to response. So like we talked about sequence-to-sequence models in machine translation before. So the basic idea was that you just feed this into an MT system, and the MT system kind of works. However, it's not so simple. And the reason why is because machine translation and dialogue are actually very different tasks with very different forms of responses. And one thing that's very different is that there's a much weaker association between input utterances and responses in dialogue response generation than there is in machine translation. So machine translation, basically you need to turn all of the content in the source sentence into content in the target sentence, but that's not the case for dialogue. So they showed some examples of alignments that they got from this. So what time is one chunk, and at 5 is the answer to this. U gets translated into I, get gets translated into get, and out gets translated into off. So you can see that this is kind of a nice example where it lines up well. However, there's other examples if anyone's still awake, let's play a game. Name 3 Kevin Costner movies that don't suck. And the answer is easier question, please. So, yeah, I don't know. This doesn't seem like it'd be so easy to, generate a completely new response for this, unless you can actually name 3 Kevin Costner movies that don't suck. But I don't know if a machine could do that. So basically what they did was they did lots of data filtering and stuff like this to ensure that the rules that they extracted were reliable and generalizable. So then the next obvious thing that you might do next, which became very obvious in 2015, which is why 3 people proposed it at the same time, is instead of using a statistical machine translation model, use a neural MT model, basically. And this can be done with encoder decoders. There's a bunch of little twists here. The simplest model basically takes the previous utterance. In this case, they were doing it in Chinese because they're a Chinese research group. So they take the previous utterance and try to generate the output. So the English translations here are a little bit awkward, so the Chinese people can tell me whether these responses look reasonable. But like, high fever attacks me every New Year's Day. Get well, students, soon and stay healthy. I gain 1 more year. Grateful to my group. So happy. Getting old now. Time has no mercy. Ouch. And we should go out with some cute guys to enjoy a great outing in such nice weather. It is indeed very nice weather. So. I don't know, for me it seems like the cute guys is the more important part here, but maybe the response is not very interested. So you can see this is kind of fun. However, there are lots of differences between machine translation models and dialogue models. And problem number 1 is dialogue is more dependent on global coherence of all of the outputs. So considering only a single previous utterance will lead to kind of locally coherent but globally incoherent responses. So it's necessary to consider more context. And one example of this is Sordoni et al., who basically did another very simple thing, which was in addition to taking the previous message, they also took 1 additional utterance before, and they encoded these 2 things and then generated the output. So this is, it's quite simple. You could do, the simplest possible thing you could do is just concatenate these 2 together and maybe put a symbol in between them. You could also have a separate encoder for the context, separate encoder for the message, and 2 attention mechanisms over both of them and predict the output. So. Actually, kind of the work in this area predated the work in machine translation that tried to do the same thing. And the reason why is simply because it's more important for this task. So there's actually interesting work that shows that context can be really important for some things in MT. And sometimes, even if you model context in a reasonable way, you can't get clear improvements on some tasks. So, as I said, the Sordoni et al. Paper considered 1 additional previous context utterance. The Vinyals et al. Paper, which I introduced in parallel, just concatenated together all of the previous utterances and fed them into 1 big RNN. And because they were Google and made the RNN really big and deep, and had lots of data, it actually kind of worked. You could get semi-coherent conversations. They didn't actually evaluate the coherence of the conversations very directly, so it's kind of hard to tell in a very systematic way, but they had nice qualitative results, which may or may not have been cherry-picked. So here's one example of such a nice qualitative result for customer service. And the reason why they can do customer service is they have lots of customer service reps who answer lots of problems, essentially, in their internal data. So Describe your problem. I'm having issues accessing VPN. Hi, hello, could you please let me know what operating system you're using? I'm using Linux. Okay, it was in the SSL VPN on which you stated it was broken. Please check if you're logged in, etc. And apparently this is one example that worked. That might be pretty impressive. I'm sure there are lots of other examples where this didn't work. So don't look at this and assume that the problem has been solved, I guess. So one way that people have worked to improve these models is with hierarchical encoder-decoder models. And basically the way these work is in addition to having a word-level RNN to read in the previous inputs and generate the next outputs, they also have an utterance-level RNN to track the overall dialogue state. So the idea of this is pretty simple. You essentially have an encoder down here that takes in all of the words of the input and encodes it into the context hidden state. And then this context hidden state is used to generate the output of what's wrong. And then you feed in what's wrong again, you get the utterance representation, and you get generate the output like this. So the idea is simple. The implementation is, you need to do lots of padding and masking, but you can implement this in a reasonable way with just like 2 RNNs, one on the bottom, and one tracking the overall dialogue state up here. Are there any questions so far? One thing I should note, actually, is that dialogue models don't necessarily use attention. So in NMT, you always use attention. It's really important to use. It's not quite so clear in dialogue models. And the reason why is because essentially as I noted before, the connection between the input and output is much less strong than it is in MT. So in MT, you can do a pretty good job between similar languages by just reading off word by word and copying, translating the words into the output. Whereas for dialogue, you get much more things like, much more abstract things like Kevin Costner movies that get translated into something that doesn't have any word by word correspondence. So you don't necessarily need attention, and you might just be able to use a single encoded state for the previous utterance. So this is a model, a discourse-level VAE model. This was actually done here at CMU by Tiangqi Zhao. And he basically encoded the entire previous dialogue context as a latent variable in the VAE. And also used meta information such as dialogue acts. So the model is a little bit, I won't say complicated, but it's a little bit more involved than the other model. But the way it works is you encode the previous utterance. You also encode things like dialogue acts and meta information that you have from the previous context. And you run this through a recognition network that tries to predict the previous, the state, I guess. Or sorry, you run it through the prior network that tries to predict the next state, and also a recognition network. And then you generate the output, I like cats. So this I like cats is essentially available to the recognition network. So this is, you want to do an auto-encoding objective where you reproduce the I like cats from this variable that you have here. But in addition to this, they have a few other things. So one other thing that they have is essentially an NLP that tries to predict the vocabulary over the bag of words, and also an NLP that tries to predict the dialogue act. And the reason why they have these things here is essentially if you just have the decoder that tries to generate the words, essentially you can kind of, this is a common problem in VAEs, but if your decoder is too strong, essentially this decoder will learn to ignore the latent variable that you get over here. And so what they did was they added a couple additional objectives that tried to ensure that kind of abstract information like the Dialog Act and also the information about all the words in the utterance was directly like encoded in the latent variables that they have here. So the alleged reason why this is good is something that I'm going to be talking about a little bit later. But one of the reasons why they suggested this is they wanted to capture the variability that you have across different dialogues and across different like ways of speaking and stuff like this. And they alleged that a latent variable model that has this essentially sampled from a distribution would give you a better way to encode this. So yeah, this is a slightly more involved model, so it's a little bit harder for me to do justice on a single slide, but hopefully this gives you the high-level overview, and you can go back and take a look at the paper if you're interested. Okay, so as I said, one of the additional features of Dialog, and this is not just the case for Dialog, this is the case for a lot of different tasks, and it's something important to be aware of, while Dialog is a good example, is that Dialog allows for much more varied responses than for example, machine translation. And the reason why is precisely because, you know, if I say, hello, how are you doing? There's hundreds of ways you could answer that, right? Whereas if I said, hello, how are you doing? And then wanted to translate, I'm doing good, from some other language into English, you know, there's only a certain number of ways that you could translate I'm doing good. So for translation, yeah, to summarize, there's lexical variation, but the content remains the same in translation, but in Dialog, the content will also be different. So there's a really nice example in a paper by Jiwei Li that says, what are you doing? And there's lots and lots of different possible responses that you could do for this. But unfortunately, if you look at the top responses according to a regular trained Dialog model, the answer is, I don't know, nothing. Get out of the way, I'm not sure why, but oh my God. And then if you say, what is your name? The answer is, I don't know, sir. Whereas you have other things like, my name is Robert, my name is John, my name's John, down farther. Also, how old are you? Number one answer, of course, is also, I don't know. So, and then farther down, you have things like 25, 5, 8, etc. So basically, I talked about this a little bit before with respect to adversarial models, and this is a problem also with like regular maximum likelihood trained models, which is they give kind of like blurry or non-informative, not very sharp responses. And you're seeing this here as well, because basically the model doesn't want to commit to something that has a low probability. Like my name is Graham, for example, would be relatively low probability. So one way that they've gotten around this for Dialog models is by introducing a diversity promoting objective. And the basic idea is that we want responses that are likely given the context, but unlikely otherwise. So they have a really simple method. I don't think this is the best method or the only method, but it is something that you can do quite simply, which is you subtract the weighted unconditioned log probability from the conditioned probability. So what this means basically is you have the probability of the output given the input, and you're reducing the probability according to just a language model. And the idea why you would want to do this is something like, I don't know. This is a super frequent utterance, right? So no matter what the context you will have, you'll get a high score for this. Whereas something like my name is Robert or my name is John, you'll only get a high probability for that given the input, what is your name? So by subtracting out the really frequent ones in any context, you can get a more diverse response. So there's an example here. I did not get the report from an MI6 agent. I don't think that's a good idea. You did the right thing, did you? I'm losing my grip. I don't know what you're talking about. I'm the only one in the world. I'm ready to help. So you can see that it's maybe nominally better, nominally more diverse. So this is something important to talk about. As I said, there's other methods. Like you can come up with methods that promote diversity in your Beam search. I'm going to talk about another method that actually went into the Google auto response thing for your email a little bit later. But this is one example that you can take a look at. Any questions about this? Any dialogue people have good recent references for this? What are people using in 2019 to solve this problem? Any idea? Yeah.
A lot of people are using personalization.
Okay.
So instead of just saying that my name is John, you already know that the person's name is John, so use that information to.
Okay, that's good. I'm actually going to talk about that later. So thanks. Okay, yeah. So that's a good thing. So personalization, which I'll talk about later, is one solution. Any other things? Okay. Cool. So next, diversity is also a huge problem for evaluation of dialogue models. And again, this is not just a problem for dialogue. This is a problem for other things where you can get various responses like text generation from structured data. Like let's say you want to generate a movie review about a movie or something like this. There's a million different ways you could write a movie review. So how do you evaluate that movie review? Translation uses blue score. Blue score also isn't perfect for translation either, but it's also it's not horrible. It does correlate with human evaluation to some extent. But in dialogue, you can see that blue shows very little correlation. So basically what these graphs are is human score. So this is how good humans judged the output to be. This is blue score. So you can see there's virtually no correlation between these two metrics. And in fact, I think the correlation coefficient is 0 or something like that. There's also embedding average. So they took the average of the embeddings in the actual response and the average of the embeddings in the generated response. Similarly, no correlation whatsoever. However, if you take the correlation between two humans, what two humans say about a particular thing, there is actually very nice correlation. So you can see that it's not impossible to evaluate these things, but standard metrics like blue just aren't doing the job. So one solution that was created very early on in this line of research is to create multiple references with human evaluation scores for each reference. So multiple reference evaluation, which is also used for translation or other tasks, basically you generate multiple possible responses and try to see how close you get to any one of them. So what they did here was they used a baseline system to retrieve nice-looking responses according to the model, to the baseline model. And then they performed human evaluation on them, upweighted good ones and downweighted bad ones, and then used the similarity to the good ones as a way to evaluate the models. So here's an example. They have context. I was about to text you, and my two cousins got excited because they thought you were Rihanna. I can imagine their disappointment. And then you can see a couple outputs here. They were very disappointed is one that was marked as relatively good. So this has a positive value here. So this is, this is the human generated response, I guess. Then they retrieved a bunch of other responses. So yes, luckily the whole thing feels very much of the past now. I guess this was graded as even better than the original response. I'm not exactly sure why. This one was graded about the same as the original response. And then you have a couple other ones, like the weather in Russia is very cool, where that was given a bad response. So basically, the idea behind the measure, the idea behind the measure is that they take these good responses as things the system should get close to, and these bad responses is the thing the system should be far away from. So the closer you are to the good responses, the better this is. So I think this is a really nice method for evaluation, and a really good way to, evaluate dialogue systems. They can actually show reasonable correlation. What's the problem with it? Any ideas?
It's a set of choices.
It's a set of choices. Yeah. It's a limited set, and you're still limiting your coverage. Yeah, that's completely true. I would argue that 5 choices is much better than just 1 choice, or 6 choices is much better than just 1. Any other things?
They should be explicitly related, like response and
They should be expressly related?
explicitly.
Explicitly. Yeah, I think that would be good as well. I was thinking about a much more simple thing, like who has the money to make this data set? I don't have the money to make this data set. If you have big data sets like this on data sets that people care about in dialogue, it's probably a good idea, but it is a very expensive and involved way of evaluating your methods. Okay. So one way to get around this is learning to evaluate. So basically the idea is use the context, the true responses, and the actual response to learn a regressor that predicts goodness. So you can view blue or whatever other evaluation metric as essentially a regressor from a actual response that a human created to a response that that the system generated. A response that a human created and the response that the system generated to an evaluation score, right? So it takes in these 2 values and gives an output. What they want to do is they instead want to create a learnable function that additionally adds the context that the system used and tries to predict the output. Importantly, this is similar to the problem that we're asking the model to solve, but instead of just having the input, it also has access to the reference. So the very simple model that people came up with is a kind of hierarchical RNN that is similar to the hierarchical RNN that generates the output given the context, but additionally has access to the true response and the model response and creates a regressor to the score here. And then another idea is essentially adversarial evaluation, where you take in either a true response or a model response, and you try to decide whether it's a true response or a model response. And the more that you can fool a discriminator, the better job you're doing at generating outputs. So in fact, this is not the first time people have thought about this. People have used learnable metrics for machine translation for a long time. I think they're good. Like this is one lightweight way to create a model that can evaluate your dialogue responses. But one caveat that we have from MT is that learnable metrics like this tend to overfit to the data set they were trained on. So if you only have a small number of things that you can use to train these models, it becomes very difficult to apply them to new fields, and they often tend to underperform there as well. Another problem with them is that if the evaluation metrics are opaque, it's very hard to tell why they made the decision that something is good or not. But it's certainly something to think about if you want to evaluate a hard to evaluate task. So something something like this, or kind of like open domain text generation or things like that. Okay. Any questions about this?
Wouldn't you decouple training and evaluation? Because it seems to be a bit strange that you're fitting your evaluated metric on the same data set.
Oh, so how do you decouple training and evaluation? Because it's strange that you would be training the evaluation metric on the same data set. I think you could make a strong argument that they shouldn't be trained on the same data set. I think one argument that it still makes sense to train them on the same data set is the evaluation metric has additional input. It has the input of the true response. That being said, I think it will, one of the reasons why it would tend to overfit is if it will, your evaluation metric will look particularly good if they're both trained on the same data set, because it's, completely IID, the data comes from the same distribution, et cetera. But you can also make that argument about any research on machine learning, like any research on machine learning that uses the same data set uses an identical distribution for training and evaluation would have this problem as well, maybe. Yeah. Any other questions?
What's the magnitude samples for this model, for the evaluation model?
Oh, so it depends which one you're talking about. For the first one, they have a bit of human annotated data, where the humans annotate whether this is a good response or not. And that can be generated either from a baseline system or from just human responses that they generated for being good or bad. That they graded as being good or bad. So in the first case, you just train a regressor to a score that you already have. For the second case, essentially, you would probably want to train the adversary on generated outputs from that particular model. So if you train the adversary on the outputs from that particular model, you're giving the adversary the best possible situation, right? It can learn how to fit the things for the model. So you can also do adversarial training where you further try to fool the adversary, but then that's a little bit sketchy from a evaluation point of view, maybe, because you're optimizing directly for the evaluation metric, but maybe that's fine. So, any other questions? Okay. So the second thing, which actually came up right before this, so it was a perfect segue into this, is dialog agents should have some sort of personality. So if we train on all of our data, our agent will become a mishmash of personalities. So I like Ji-Wei Lee's papers because he gives really good negative examples for his baselines. Message, where do you live now? I live in Los Angeles. In what city do you live now? I live in Madrid. In which country do you live now? England, Hugh. So all of these are completely, factually inconsistent and don't make sense from the point of view of a dialog agent. So of course we'd like our agents to be consistent. So there's this really good paper from before neural networks that still I haven't seen any paper that does quite as good a job at generation based on personality. This is one called Personage. And basically they train a generation system with controllable knobs that are based on personality traits. So they take the big 5 personality traits, and they have an example where you can basically take the extroversion knob and go all the way from 1 to 7, where they start with somebody who's supposed to be very introverted, all the way up to somebody who's very extroverted. So somebody who likes to be by themselves and not talk with other people versus somebody who likes to talk to other people. So you start with a very introverted person and you see, Oh, and another thing that's interesting about this is conditioned on a dialogue act. So they're trying to say the same content with different types of realizations. So the dialogue act here is that the restaurant La Mairesse is actually a pretty good restaurant with some other additional information. So the very introverted person says, it seems to me that La Mairesse isn't as bad as the others. All the way to right, I mean, La Mairesse is the only restaurant that is any good. And then the super extroverted person says, basically, actually, I'm sure you would like La Mairesse. It features friendly service, an acceptable atmosphere, and it's a French, kosher, and steakhouse place. Even if the price is $44, it just has really good, nice food. So I think this is a really nice paper that is kind of exciting. But one of the reasons why you might not want to do this is there's lots of kind of rule-based engineering and things that go into the realization model here. So a simple way to do something that is somewhat similar is a persona-based neural dialogue model. And the idea is very simple. For each speaker, you just learn a trained embedding. And you model the speaker in embedding space and concatenate the speaker embedding with the utterance every single time. So you have the speaker embeddings and you have the word embeddings, and you just feed both of them as input into your model. They also have a speaker addressee model. So the idea being who the speaker is speaking to. So then you feed in both the embedding for the speaker and who the person is speaking to. So this might give an example of the difference between me talking to the students in this room, to whom I talk about neural networks, and me talking to like my daughter, who I talk about like toys and poop and stuff. So this is interesting. This is an interesting kind of simple method here. I think an interesting challenge would be how do you essentially make this into something that's a little bit more controllable and not just say I want to be Rob, but say I want to be an extroverted person or an introverted person or something like that. Okay. So that's all I have for generation for the moment. Are there any questions here? Yeah. Sure.
Is there any intuition why you insert the personal embedding at every token, not at the beginning of the...
Why would you do this at every token and not at the beginning? That's a good question. I feel like adding it more directly at every time step makes it easier to pass the information over long distances. The implementation is a little bit harder because you actually need to add another embedding to the model. So if you just add a tag at the beginning of the sentence, like you literally don't have to change your code. You just have to, add the tokens. Yeah.
How do you train the speaker embeddings?
So these are just trained jointly with the model. So specifically, actually, I'm sorry, I should have talked more about data, but they trained this on Twitter data, where you know who the speaker is for every dialogue act that you have. So you'll notice they have a vocabulary of 70K, so they can model 70K speakers, and they can model any other speaker that they have. Actually, I might, whoops. I should mention that we also, one obvious problem of this is that you can't model any speakers who are not in your input. And we have a paper, maybe there's other things for dialogue, but we have a paper for neural MT that could be applicable here, where basically we model the speakers as essentially a very low dimensional mixture of multiple aspects, which might get you a little bit of the way to something like this. You could view somebody as being like a mixture of their personality traits or something like this. But essentially the idea here is that you do have data for each speaker that you want to model, and you have enough data that you can learn an embedding and use that for the future. Yeah.
Can you talk a bit more about the previous paper, the Mairesse paper, or how does that work?
Oh, how the MT related one works?
No.
The-
paper which had the norms for extroversion and introversion.
Oh, okay, sure. Yeah. So I should probably open up the paper just so I can give some concrete examples. So this is the name of the paper, Personality Generation for Dialogue, and they use a very standard old school dialogue system where you have content planning that is based on, I'm going to talk about this more later for people who don't understand this, but you have content planning where you choose the communicative goals like the dialogue act. Then you have sentence planning where you choose the linguistic realization, what kind of lexicon and syntax you use. And then you actually generate the output. And they had a rule-based system where where basically the generation system has a bunch of parameters like verbosity, restatements, repetitions, content polarity, repetition polarity, etc. And then they map all of these parameters of the generation system onto the personality traits. So they not only do generation, but they also do recognition. I don't know if it's in this paper, in another paper, but they also explain how they recognize the traits, and they essentially have a regression tree. Okay, so here I think they're doing essentially realization. Recognition of the personality traits, where they train a decision tree based on all of these various recognized aspects of the utterance and regress to, I'm not sure what M5 prime is. Oh, yeah, extroverted. So they do recognition like this, and then you can also map from the extroversion buckets back into the, the various traits that you feed into the generation system. So yeah, it's a very well done paper, and he has like several papers in this, or they have several papers in this general thread. Okay. Yeah, actually, sometimes the interesting papers are not the neural network papers, but the ones that you could think of how to map them into a neural network paper. So, any other questions? Yeah.
Yeah, it's kind of high level, but like
Sure.
I want to know what is the assumption we made about the personality of the users in the data set. Like say, the model will learn more about people who tweet a lot, but know less about people who tweet less, and there's the personality of the people may be shifted over time. Say if I look at the tweets that they posted 2 years ago, I may be confused like what guy it is, and so I wonder like whether the embedding of personality we made will you could like map to the real personality in the real world, or some like whether we consider such changes in.
So do we consider changes in the personality? I'm certain that this paper did not do that. There might be follow-up papers that do that. I'm not aware of any. But that's a really good point. People change in their personality, they change in the vocabulary they use, and modeling that change in some good way would be good also. The fact that we don't know much about people who don't tweet very much, that's another, really good point. We might, you might want to use other sources of information about that person if you wanted to, or more abstract sources like their demographic traits or something like that, to make sure that you generalize better across people. It's quite possible that embeddings would capture demographic traits if you had enough, data to train on them, but yeah. So actually, I intended to add a slide, and I just realized I forgot it. Let me see if I can find. So there's also a paper recently. This is a kind of interesting task that was created as part of the Parlay challenge. And the idea being that you have a natural language description of a person here. So persona 1 and persona 2, these are written in natural language. And then you want to, you basically want to generate an output based on this. They have a data set for this, and I think it's a kind of interesting challenge because it does restrict the space of the possible responses you could expect. It's still an extremely under-constrained problem, and you'll still have problems with evaluation, et cetera, but at least you can do that. And also you can kind of evaluate whether the response actually makes sense. And you're not just like regurgitating something that you've already seen in the training data. So if you're interested in this, this is a nice data set that a lot of people have been using recently as well. Okay. So I will move on to the next part. So this is retrieval-based models. As I mentioned, these are a little bit safer, but maybe a little bit less flexible. So dialogue response retrieval, the idea is that many things can be answered with a template. So you simply find the most relevant response out of existing ones in a corpus. So this is the Google response generation. Thanks to this, I now can answer about half of my emails by clicking a button on my phone for Gmail. When one of my students asks me, do you like method A or method B, I can write, sounds like a good idea, or no. Recently, I've started to be able to figure out when people are using this to respond to me, because it sounds strangely unnatural that that person would use that exact wording when they respond to one of my emails. So I think this is also shaping the way we speak or the way we send email as well. It's kind of an interesting sociological thing. But anyway, this is super useful though. Like a lot of the time it's right, and a lot of the time I can just write an email by pressing a button. So retrieval-based chat has been around for a long time. It was called example-based dialogue systems for a while. And the basic idea is given an utterance, find the most similar one in a database and return it. Early work on this basically just did really simple retrieval models, information retrieval models like TF-IDF, weighted cosine similarity, et cetera. Maybe you abstract away location types, et cetera. And also discourse history vectors. So this is kind of an interesting thing. They also measured the discourse history based on like what kind of dialogue acts you've seen so far and stuff. And like everything else, this was turned into a neural network. In this case, it was actually one of the students I was working with who turned this into a neural network. I think we actually had the first neural dialogue system. This is my humble brag time in 2014. So we used neural models to soften the connection between input and output and do more flexible matching. So basically the idea is neural TF-IDF based cosine similarity retrieval isn't flexible enough to capture more complex patterns. So we took a paraphrase recognition model and basically applied this to calculate the similarity between the utterances. And this did a better job than regular cosine similarity. Yeah, and it used a model based on recursive autoencoders and dynamic pooling to do so. So this has been scaled up by Google, and they actually have a really nice paper on this. The reason why I think this is a really nice paper is this essentially goes into a lot of the things that they had to do to make this a practical system as opposed to something just in the lab. And it's implemented in the Gmail Smart Reply. They actually use a retrieval model, but it's based on an LSTM-based sequence model. So it's a model that could also be used for generation, but instead of using it for generation, they're using it for retrieval of existing responses. And the reason why they're doing this is because they don't want it to suddenly output things that could be extremely offensive. So they have a pre-curated set of responses that they know are okay to output as dialogue responses. So what they do is they essentially do beam search over the response space, but the beam search over the response space is limited to only things that actually exist in your database. So what you can do is you can build a big trie. People know what tries are, right, from your data structures course. So it's basically a tree that encodes all of the prefixes that you can have. You score all of the prefixes with a sequence-to-sequence model until you get an output. They also canonicalize syntactic variants and cluster together similar responses. So if you have, I do not think that's a good idea, and I don't think that's a good idea, these would all be combined together into a single cluster. They have human curation of the responses, as I said, to prevent Google from getting in trouble. And they enforce diversity through omission of redundant responses. So they don't output anything that's in the same cluster because they only have 3 responses and they want to make sure all of them seem good. Also, anytime they output something that's either positive or negative, they also output a negative thing. So the idea being that if somebody's asking you whether you think it's a good idea to do something, they make sure that you have at least one response that says yes and one that says no. So that's also a good thing because then, at least the human gets to choose between responses that don't mean the same thing. So this is really cool. This is an example of a neural dialogue system that people are actually using, every day for large-scale things. Any questions about this? I actually don't know of any other example of a neural conversation generation system that's used every day for things. Like there are chatbots like the ones created by Microsoft. Famously, I'm going to pronounce it very badly, but Shell Ice in China, and in Japan they have a similar one called Rina, and what was the one in the U.S.? It was like K or Tay or something like that. That was up for a very short period of time in 2015 until they had to take it down because people taught it how to hail Hitler and other really bad things. So this human curation of responses, I think, is really, really important if you're scraping data from the web. Because if you train things on Reddit, for example, or Twitter, you will very quickly become very disenchanted with humanity and realize how horrible some of the corner case things are on the web. So yeah, that's something to keep in mind if you actually want to deploy something to users. Like if you form a startup or something, be careful with this. Okay, so moving on to task-driven dialogue. So task-driven dialogue, as I said, this is not just chat, where chat is to keep the user entertained. In this case, you want to do an actual task. So book a flight, access information from a database, etc. This is another type of dialogue system that you interact with, maybe not on a daily basis, but perhaps on a monthly basis when you call into a call center or something like this. You probably are very frustrated by these systems on a monthly basis whenever you call into a call center. At least I am. So the traditional task completion dialogue framework is based on kind of semantic frames. So what you do is you do natural language understanding, where you do some sort of information extraction from the utterances that the user made. And you try to fill in the slots in a frame based on the user utterance. An example of this frame, if you're resolving a, if you're trying to help a user book a flight, might be what is the flight that they want from where to where. So from and to, like departure and arrival would be 2 slots in the frame. And you might want to fill them in or say, I don't know what the slot value is. Dialogue state tracking, in contrast to natural language understanding, which is usually over a single utterance, dialogue state tracking is tracking your belief over what the user wants over multiple turns. Dialogue control then takes in the dialogue state to decide the next action based on the state. And natural language generation generates utterances based on the current state. So there are lots and lots of systems that follow this general paradigm. In fact, probably most actually deployed systems follow this paradigm. The problem with this is really hard. Like, how do you define all of the slots that you would need? How would you track dialogue states? And this is particularly important in spoken dialogue systems, which are a great portion of the dialogue systems, because you have ASR errors, for example. So you might not know whether you want an Italian restaurant or if you want to tally a restaurant or something like that. That doesn't make very much sense. But like ASR errors make this a very hard problem. Also, deciding what to do next under this uncertainty is hard as well. So all of these like individual components have been neuralized. So natural language understanding can be done by training beginning in out taggers, BIO taggers, in the same way we would do something like named entity recognition. You also have things like intent and domain classification. So these are telling you what task you want to be doing in the first place. So intent and domain classification are particularly important if you have kind of an open domain task-based dialogue system like your phone. So if you're speaking to your phone, it can open any number of apps on your phone, right? And all of those have their own individual slots. They have their own individual dialogue control. So first you classify the domain, which might be an app. Then you classify the intent, which is like what functionality of the app do you want to call. And then you also select the concepts, which might be the arguments to the function that you want to call. So this is another way of thinking of this. The implementation details aren't super interesting. It's an RNN CRF based on for the tagging. Dialogue state tracking is a little bit more interesting. So what you want to do is you want to track your belief about the current frame filling state. So the idea being that if you say, hello, which bus route, and somebody says 61C, you output a bunch of examples, maybe susceptible to ASR errors. You have confidences over them. You have pre-hypothesis features. Then you combine them into a hypothesis. You have a bunch of different beliefs where this is kind of a probability distribution over what you want to do. So then your model realizes that it's not very confident in the output. So it says, sorry, could you confirm? So basically it picks another one, and then you say 61C again, etc. Oh, if these bus numbers look familiar, they're from here in Pittsburgh. This is based on a data set created by Ellen Black and Maxine Eskenazi here at CMU that was used for a long time. It's the Let's Go corpus. So if you want to go use this, you have an advantage over all the other researchers using this data set because you know the bus routes already. Not a very big advantage, but maybe an advantage. So Henderson et al. Present an RNN-based model that encodes multiple ASR hypotheses and generalizes by abstracting out various details. This is a pretty nice paper. I don't know if this won the best paper at SIGDIAL or something like this, but it's a pretty good example of how you can do this in a well-engineered way. Then the language generation part, of course, this has also been neuralized. This is maybe one of the things that has been a little bit more successful, maybe. Basically, it's an LSTM-based model. Back when LSTMs were kind of new things in NLP. And you basically condition the LSTM units based on the dialogue input, output, et cetera, and the output English, et cetera. The details, you can look at it. They're not super important. It's just a nice example of an LSTM-based generation model. So all of these are really good. And like, let's say you want to found a startup that's doing dialogue systems. Probably the first thing you'll do is try an end-to-end model and fail miserably and fall back on the on the old on the old methods. Maybe you won't fail miserably, but a lot of people have failed miserably at this, despite being very smart people. But kind of the really maybe exciting thing in this space is, can we take the general architecture of the models that are used for these kind of traditional dialogue systems, but can we learn the dialogue control in an end-to-end way? So basically what they do is they train an LSTM that takes in text and entities and directly chooses an action to take, where the action can be either kind of a chatbot style response or an API call to the API calls that we want to be able to handle. So specifically, as I said before, they did this in the domain of smartphones, where you want to do smartphone control. They have this big kind of semi-complicated pipeline where you do entity extraction, entity tracking, utterance embedding, bag of words embedding. You do an RNN. The most important thing here is the fact that you have predictions over not just output utterances, but also API calls like forecast, where forecast is a call to your weather forecasting app. And then they choose the action template. Based on the action template, if you want to forecast the weather for Pittsburgh, then you need to fill in the arguments for this API call. So then you fill in like Pittsburgh from your entity tracking model here. You choose whether to do API or text, and then based on that, you make a deterministic choice whether this is the API call or text, and then you output either a nice weather report in your smartphone or an audience here. They train this using a combination of supervised and reinforcement learning. So they start out by doing a bunch of Wizard of Oz simulations, where they have a user interact with the system like it were an actual user, like it were an actual system, but actually you have a human behind the scenes doing all the actions for you. And then they essentially deploy the model to users and train it using reinforcement learning based on on various metrics. So that's all I have. I think this is a really exciting development. Honestly, I don't know. I haven't gone back to review how this has developed in the past year or so, but I thought this was a really good paper when it came out. So this might be a good place to start if you actually want to build something that people are using in a practical setting. I think the idea of mixed mode output, where you kind of fall back to text when you don't know what to do, but when you do know what to do, you get it into API calls over the actions that you're interested in, is kind of an interesting way for doing this. Yeah, and if you could even, like, if things don't go well, you could even just fall back on API calls, where the API calls go to a deterministic text generator, for example. Okay, that is all I have for dialogue. Are there any questions? Follow-ups? Any important things that I missed? Yeah? Oh, just scratching? Okay. Ah, man, I thought somebody was going to tell me something really cool and interesting. Oh, well. Okay. Okay, well, thanks. I'll finish up here.